Thank you for taking the time out of your day to join our talk. Today we will be speaking on multi-tenant SaaS applications made simple on Azure Cosmos DB for PostgreSQL. And I know that SQL Bits is about SQL Server, but we thought that perhaps you want to have some change in your life or see what the future holds. So we are here to tell you about that. So my name is Adam Volk. I am a senior program manager for Azure Cosmos DB for PostgreSQL, and more precisely the Citus database extension for PostgreSQL that is used with the service that Microsoft provides from the service. And here's Alicja Kucharczyk.
Yeah, hi, my name is Alicja Kucharczyk, and I'm program manager in Azure database for Postgres flexible server team.
Cool.
Okay.
So today we will speak about software as a service. And what do we mean by that? First of all, for me, that squeezing out the margins out of your hardware and making money by providing your hardware to multiple businesses on the same infrastructure. So with multi-tenant software as a service, we expect you to have the same software, the same infrastructure, and multiple businesses and customers benefiting from that. The customer from this obviously takes the ease of operation. They don't have to code the complex software, they don't have to maintain the infrastructure, and you as the operator, you have that hardware margin. You efficiently use the hardware by making money. And a lot of people assume that this is a new model. It's often associated with startups doing like software as a service. But if you go back in time to something like 1995, you will find these plethora of email hosting providers that did shared email hosting, where you would come in with your own domain, they would provide you the storage, and they would find out that, for example, having only a 100 gigabyte hard drive, they could tell you that we will give you a 10 gigabyte inbox. And that inbox, while they don't have the storage to provide a terabyte of data for everyone, they can pretend they have it, like in a fractional banking system where the bank lends out money, just holding a fraction of the actual value that they are lending out. In a similar way, these companies were relying on the fact that most people will not fill up those 10 gigabyte mailboxes. So if you look at the pitiful graphic on the right that I tried to do, the boxes above represent a web browser. The envelopes on the left represent emails going into such a system, and the big DNS box is a horrific simplification of what's in the middle. But the point is that this was the decision point, where somebody came in from their browser with the darker blue color, and it was, for example, for foo.com domain. And the system knew from the DNS resolution that this is a tenant, and we should show that tenant the email stored on the drive in that specific place. And in a similar way, when an email envelope came into the system, it was routed to the specific storage space. So back in 1995, we all were doing multi-tenant systems, and we can do the same with databases. So with databases, you have sharding models. Now, this conference is D&D themed, and I can't not mention one of the accredited sources for the name Sharding. I don't know how many of you know about this, but there was a game called Ultima Online, and in that game, that was a massive multiplayer online RPG, where in a D&D-like setting, not D&D itself, but like a fantasy setting, where they wanted to scale. And they had databases, they had servers, they had to scale to massive online amount of players. So they came up with, like, how do you distribute databases? But they had to justify to the players what to call it. Like, how do we explain that if you pick a specific server, you won't be able to play from a friend from Europe that picked another server. So the justification they found for that was that there was this evil wizard mundane that entrapped Susaria, which was the realm in the game, in a crystal. And when the player beat the evil wizard at the end of the game and shattered the crystal, the world was fractured into shards, each one of which contained a copy, a refracted copy of the realm, of the whole Susaria. So that's how they explained sharding, and that's one of the accredited sources of the word sharding in databases. So if we talk about sharding, there are various ways you can do sharding, and that's true in all databases. So you might map it to whatever you use. I'm speaking in terms of PostgreSQL, which is an open source database that Alicja will explain in a moment. But going through the models themselves, there's row-based sharding, which means that you have your database schema, and in every table in your database schema, you have a column that you decide is the distribution key. And usually that's a tenant ID. That could be a domain name, for example, in an email-like system. And based on that column, you would modify your application to have that column in every table, and you would modify your application code to contain that column in every workload of your queries. And that way, you can place the various parts of each table on different machines and route the queries to the specific machines, achieving horizontal scale, because sharding essentially is horizontal partitioning of your database. So with row-based sharding, with PostgreSQL, a back-of-the-napkin calculation shows you that you can have 100,000 tenants per 16 VCP node. And the drawback of that is you have to adjust your schema, and you have to modify every query of your application to contain that distribution key so that you can narrow down your queries to specific shards. And that gives you the best hardware utilization. This is the model that allows you to squeeze out the margins in a similar way that the email hosting providers did. Another model that you have is schema-based sharding. And in that model, you have the benefit of not having to modify your schema, not having to modify your application code very much. You just take your existing application. For every tenant in your system, you create a new schema, and you essentially switch the active schema based on a decision point. Like, for example, in your middleware software, you find that the person landed on this specific domain, so you set the schema to that tenant, and the application doesn't need any additional changes. Now, again, back-of-the-napkin calculations show that with PostgreSQL, you could fit 4,000 to 5,000 tenants per a 16 vCPU node. The benefit of that is no schema changes, no query changes, and that allows you an easy lift and shift operation for like taking your legacy application into the cloud, into a multi-tenant system. Now, why such low numbers of tenants? PostgreSQL has something called catalog tables. So for every table in your application, you would have entries in those catalog tables, and for every row in those tables, you would have additional entries in other catalog tables. So that's some metadata that PostgreSQL itself keeps to track things. So if you have a large amount of schemas, you have to multiply said metadata by the amount of schemas you have. So that can grow very quickly, and that's the additional overhead that the internal mechanisms of the database engine have to go through to manage things. And the final model that some people might, coming from other databases, often think that makes sense with PostgreSQL is database sharding. And with database sharding, the problem is that with PostgreSQL, you can only fit up to 100 tenants per a 16 vCPU node. It provides you the same benefits as schema-based sharding, which is no schema changes, no query changes, but that's the highest operational cost, unfortunately. And the problem with PostgreSQL for that is its architecture that originated in 1985, where for each database connection, the system spawns this operating system level process. So the connections are quite heavy, and connections are database bound. So if you have a connection limit, which is a normal thing in PostgreSQL, for example 10, and that's just to have it easier to speak about it. So with a connection limit of 10, you can either connect to 10 different databases and keep each connection alive, or connect to one database 10 times, keeping 10 connections open to that one database, but you won't be able to open another connection. And even if you implement a multiplexer for connections, which is often done in PostgreSQL using tooling like pgbouncer, which is a connection pooler, then with database sharding, that pgbouncer won't be able to multiplex over the whole pool because it has to keep that isolation between connections and databases. Whereas if you use schema-based sharding, then with a pgbouncer, it could keep one connection open and multiplex it over the 10 schemas, because that connection is not bound to one schema. That's the difference, and that's why the overhead is so much. There are also other processes like vacuuming and other things that PostgreSQL does that add to that limitations. There are also some misconceptions. For example, PostgreSQL uses write-ahead lock, a wall that's shared across databases. So even if you go database sharding, you can do things like point-in-time recover a single tenant. So some assumptions that people make on the isolation guarantees and functionalities the database provides are not essentially true in that scenario. But I have been mentioning PostgreSQL a lot and Citus a lot, and this is a SQL Server conference. So I will kick it off to Alicja to tell us more about the database itself.
Yeah, thank you, Adam. So I would like to start about just a very quick description. What actually is Postgres? And starting from that, as you probably noticed, Adam has used PostgreSQL name, but also the other name that you're absolutely free to use is just Postgres. But please don't forget the S at the end, okay? So we've got PostgreSQL or Postgres, okay? And what is actually this database? So database that we call Postgres. It's a fully open source, and also it's not owned by any company. It's not owned by any foundation. It's a fully open source code that a lot of people around the world are working on together. And it cannot be owned, and it cannot be bought by any companies, what happened a couple times in the past for other open source technologies. And you've got a full ACID guarantees. So this is relational database, similarly to SQL Server. Actually, Postgres and SQL Server has got some common roots. It's not the same database because over the years, there's been a lot of changes in both engines, but basically they do have the common ancestor. Postgres is especially well known for its extensions. So it's not like in other databases that you've got a huge database with a lot of features out of the box. Postgres has got a bit different architecture. So we've got really small Postgres core, and then we are able to add extensions. For instance, if you would need encryption, then you've got pgcrypt extension. If you want your database to have to store geospatial data, then you've got really famous PostGIS extension. And like another extension is Citus that Adam already mentioned, which is actually open source, but the company that is like that authored the extension and still working actively on the extension was acquired by Microsoft. But still, still this is open source, and we are not gonna, and we don't have absolutely no plans like to make it closed source or like starting to license the extension. We've got a rich set of the indexes, like of course, like the classic, for instance, B-tree indexes, but also Gene, Breast, GIS. We obviously support the window functions. We support CTEs, so the queries like with starting with the with keyword. Full text search and also JSON-B, which is something not common with relational databases, although like other databases also like keeping up now with that. So with the JSON-B, which some people like think that B stands for brilliant, it's actually binary. But of course, like this binary version of JSON is brilliant, okay, I totally agree, like most of the people would agree. So we don't store JSONs as the text in the database. It has like its special data types, which is JSON-B. It's got a lot of indexes on top of that. It's got the storage footprint is much smaller than it would be for the text. And also another thing that Postgres is really famous for, it's the rich data types. So if you just have like Postgres core without any extensions added, you would have over 80 different data types. Recently, I saw that Oracle is trying like to keep up with Postgres in the data types area, so they finally added Boolean to Oracle. Yeah, bravo for Oracle. But Boolean for like in Postgres was like for years, and like it was heavily used in Postgres. We've got PGStat statement is another like very popular extension, although I do prefer PG Badger. This is like you can track your queries that are happening in the Postgres database. And what we've got on Azure, we've got a managed version or versions of Postgres. One of the version is like a flexible server, which is like just one instance Postgres, so normal Postgres that you would install on-prem. But we also have Azure Cosmos DB for Postgres, and this talk is about Azure Cosmos DB for Postgres, which formerly was, the name was Postgres Hyperscale. And this is actually also an open source Postgres again, with the Citus extension added. And the Citus extension is like turning the Postgres into distributed, horizontally scaled out engine. Both are PaaS services, so both are managed by Microsoft. And let's go a bit deeper about Cosmos DB for Postgres. So as I said, it's built on open source Postgres version. So it's not a fork. It's not like we changed any code. Like the ability to distribute across multiple nodes comes from the extension. So we're just adding the extension to Postgres open source. And then you've got this ability to use multiple nodes, VMs, instead of just a single instance. And all those nodes are connected in the smaller or bigger cluster. It could be really big, like up to petabytes. But basically, the idea behind that is that you've got multiple Postgres instances connected together. And one of the main use cases for Cosmos DB for Postgres was what Adam just said. So multi-tenant SaaS applications. So it was built like for this particular use case from the very, very beginning. And what also cool about this particular technology that you can start really small with just 10 20, 50 tenants. And then while your company is growing, while your business is growing, then you can add the nodes and make your database bigger and bigger. And all the operations actually, except of the vertical scaling, you're able to do online. So you're able to add, to add nodes and also spread the data across the nodes in using the online process, so without any downtime for the application. Okay, and terminology, because before we start, we would like to just to explain 4 very commonly used terms that we used with Cosmos DB for Postgres. So maybe Adam, you start with the coordinator.
So the coordinator is a special node that we have in Azure Cosmos DB for PostgreSQL and in Citus. And I will sometimes use the extension name for short. But the coordinator is a special node that, as the name suggests, coordinates all the traffic. You have to use it for DDL, like if you want to create a table, alter a table, change an index, you have to go through the coordinator. But for any other type of query, you can go directly to a worker node. So what's a worker node?
Yeah, thank you. So yeah, we should probably have a picture up here, but I could not find a picture that would fit into this black design of the slide, so sorry for that. So you've got this one Postgres instance, which is coordinator, and then you can have 0, so just a coordinator, or multiple worker nodes, which we also call data nodes. Data nodes because the actual data should be on the worker nodes, not on the coordinator. And each of the worker nodes is actually a Postgres instance. So on the worker nodes, you might think of it like VM, for instance, with Postgres installed, and those all coordinator together with worker nodes would create a Citus or Cosmos DB for Postgres cluster. So actually, there's going to be one Postgres from your application point of view. Your application would see just one database, one Postgres database. And sharding?
Yeah, and sharding, as we explained, you can think of it as a shard from Ultima Online, but essentially sharding is horizontal scaling of your database or horizontal partitioning. So in Citus, we take a table, we do the row-based model currently. So we take a table, we pick a distribution column, we do deterministic hashing of the distribution column, which places each row based on its value of that distribution column into a bucket, which we call
shard. Yes.
And?
Yeah. And the shard, you can think of a shard as actually a Postgres table. So shard is in fact Postgres table, but this Postgres table would not contain all the data from your table. It would contain only subset of rows. So it's something similar to partitioning and the partitions, because in Postgres partitions are also separate tables. But the difference between partitioning and shards is with partitioning, you've got everything on one node, and up here you spread those shards across multiple worker or data nodes. Okay, so this is what we call the shards. Okay, so if you would like to start designing your app using Azure database, Azure Cosmos DB for Postgres. Yes. This is a new name, sorry, so I'm still having problems. Then the first thing that you need to do is the data modeling exercise, because unfortunately it's not automatically you are just putting all your data, all your system on Cosmos cluster and everything would work well. You need to do a data modeling exercise. And probably the most important step up here is to pick a right distribution key. And if you are familiar with partitioning, its process is more or less the same, maybe except of cardinality, because cardinality is really it's really important one, since it's gonna define the limits of your scalability. We cannot, if we would go from the email example that Adam was talking about, if we, as the distribution key, we would use status of the email, then we can go maximally like up to number of statuses when it comes to the shard numbers. Okay, so I don't know how many, 5, 6 probably email statuses, like something like that. So we need something, a column that has pretty good cardinality, which would enable us to split the data into like much smaller buckets. And if you would have like not the email, but maybe the flights data set, then country, like we actually have been checking how many countries are in the world. I was sure it's a bit more, but it's
195.
Yeah, 195. I was sure like it's much more, but okay. So that would not really be a good distribution key because you can go up to 200, almost 200 of the shards. On the other hand, like destination or origin airport is a bit better because, of course, like in a country, and like you would have multiple, usually airports, so you've got a bit more, right? You would have like a bit more unique values. But unique carrier has got even more unique values. So in this specific data set, the unique carrier would be probably the best distribution key. And the other thing like you need to think about it's that if your application is like querying the data, in the perfect scenario, it would hit just one node. So let's take the customer ID or tenant ID or like something similar. Then if you split client ID and you know like all your queries are using this client ID, then you probably would get the reads just from one of the nodes. Also, we would like to spread the writes to multiple nodes because in opposite to other similar solutions, especially other managed services in the cloud, Citus, so Cosmos DB for Postgres, is able to spread not only the reads, but also writes like among the nodes. And let's take kind of IoT use case. So probably a very tempting approach is to use timestamp as the distribution key. But when you've got a write and you are like gathering the data from thousands of IoT devices, then you would have a very hot partition, very hot node, worker node, that is doing at particular time all the writes, right? Because we just use timestamp. So in this case, device ID would be much better because let's go back to those points, filters reads to single nodes. So probably you are like reading, you are trying to retrieve the data about particular device. So using device ID, then with the reads you hit one node. But if you are writing like the data from multiple devices, then you would also spread the writes across all the nodes. Right? So device ID in this case would be more better.
And you still can partition the data on every node because this is underneath a relational database. So you can partition by timestamp on every node, but fan out your writes by distributing on the device ID.
Yeah, exactly. So also this is a very important point that in Postgres you've got partitioning, and by adding Citus extension, you don't really take away the ability of doing partitioning, like the ability to doing also other stuff that you can normally do on Postgres. You can still add extensions, you can still use multiple, your favorite way of writing the queries. There are some small limitations, but yes, they are not like we are taking away, for instance, B-tree indexes or something like that. And in the Citus cluster, we've got 3 types of the tables. The first one, the most important, and probably like this is where the entire magic sits, it's the distributed table. So this is the table that you can distribute across multiple rows. multiple nodes. Then you've got reference table, which is a table that is being replicated to all the nodes, and it's totally not sharded, partitioned in any way. And then you've got local table, so you should probably have really a few or even 0 local tables, because those tables are placed on the coordinator node. They are not being distributed in the cluster. They just stay on the coordinator node. And yeah, let's start from the distributed tables. So for these tables, you need this distribution key. So for instance, you have chosen device ID. And what Citus would do, let's look at the last line, so this select statement. You would say create a distributed table, give like the table name and the column name, which is actually your distribution key. And what Citus is doing is splitting your huge table into multiple smaller chunks, smaller tables, which we call shards, and then spreading those shards across multiple Postgres instances, across your entire cluster. And usually, although this is not like a hard limit, you would make tables that are larger than 10 gigabytes as distributed. Of course, it's not hard limit. Sometimes you would have like a table of this size that you would make reference, but more or less like this is rule of thumb. And you would share on the same key. Like actually, the perfect scenario would be if you would have a distribution key that is like that is already present across every and each of your tables. That would be the perfect situation if you already have that. If not, then we need to do some backfilling. And what you see as the second point, all tables are be co-located, which means if you've got table A and table B and you are using the same distribution key, then it means the values that are the values would be on the same worker node. So from both tables, you like let's say tenant ID would be 4, and all those data that are connected to tenant ID 4 would be co-located on the same worker node. So that's why this kind of architecture enables you to do really fast joins, because those joins would hit just one worker nodes. And like some example tables might be transactions, events, orders, those huge tables that you want to distribute across multiple nodes. Then let's go to the second type, which is reference tables. And I believe the best example here would be dictionary tables. So a table that you would like to have on each and every node, for instance, to do joins using this table. So for instance, something like countries, categories, and these tables will be replicated to all of the worker nodes. So each write will have some additional latency, because when you write, you need to move the data, replicate the data to all the worker nodes. And yeah, this is especially done for the efficient joins. So if you've got distributed data, like data of device ID 4 on worker node, but you would like probably all the dictionary tables to have also like in whole in the same node. And you also have like very simple function. You are just saying to Citus, create reference table, and just placing like the name of the tables that you want to be a reference one. And the local tables, so if you forgot to use any distributing, if you forgot to use any of those two functions, so either distribute your table or make a table reference one, then your table would land on the coordinator node. And unfortunately, some people just simply forget to use the function, and the tables, instead of being distributed, they landing on the coordinator node. But there is a use case for that. Like, for instance, if you've got some tool to manage the schema migration, DDL changes, then probably absolutely makes sense just to have it on the coordinator node. And like, since 10 minutes has left, as I see, sometimes, unfortunately, you would need to modify your application to be able actually to make your data distribution efficient, which means you need to backfill some data. You sometimes need to modify your primary or foreign keys, and also sometimes add somewhere closest to your application queries. So it's not totally free. It's, as I said, it's not automatically moved from one Postgres instance to the Cosmos DB, but it requires some initial work. Yeah, handing over for monitoring to Adam.
So now that you did all the hard work and you have your application distributed and you're running this in production, then you're starting to feel the need to know what's happening, like what's the pulse of the system. What does it mean that this specific node is utilizing so much memory or CPU? Why does it happen? Is that healthy? Because if you think about it, if suddenly you take a big table, split it up, put every part of that table on a different machine, and suddenly you have traffic coming in and some of it goes to one machine, some of it goes to the other, how do you know if that's okay or not? Like, do we have a noisy neighbor problem and things like that? So, upcoming in Citus 11.3, which is scheduled for somewhere around early April, which is the extension that we ship underneath the service, we have a feature called multi-tenant monitoring, where we want to provide you with the ability to have insights on both query counts per tenant and CPU usage per tenant. So you would be able to know exactly that this specific tenant generates this amount of queries of like update, select, insert, or delete type statements, and every such query used this amount of CPU, and that's enough. For example, 5-minute window rolling information, and that window size will be configurable. So if you look at the pathetic graphic on the right again, sorry, I'm not very talented, you can imagine that the 3 circles are nodes in the cluster, and the squares are tenants in the cluster, and the bright blue is the CPU utilization, and the dark blue is the query counts. So we can see that the first node gets 2,000 queries and has 10% CPU utilization. The second node gets 1K queries and 80% CPU utilization. And the last node gets 100K queries and 80% CPU utilization. So if you just had that CPU usage on the nodes itself, it's hard to tell, like, is this healthy if you don't see the other values? Like, is the first 10% okay? Are they both 80% equal? And if we look at the two 80% nodes, we see that one of them has only 1K queries, uses 80% of CPU, and has 2 tenants, and the load is evenly divided, both in query counts and CPU counts. So you can wonder, why is it only able to handle so little amount of queries, and if that's okay in CPU utilization, but maybe that's okay. But if you look at the third node, and you see that it takes 100K queries, and one tenant is taking 99K queries, and using only 30% CPU, then what happens with that one tenant that makes only 1,000 queries, then uses up almost all the CPU on that node? That sounds like a noisy neighbor. And what can you do in a situation when you have a noisy neighbor? So a noisy neighbor is like in shared systems, you share hardware with other tenants. Like in the email, there will be that one guy that decides to use his email as a Dropbox, right? Like, let's load all my files into unsent email, and that's my storage. And suddenly you have that one person that stores 50 gigabytes on their mailbox. So that's a noisy neighbor. Everybody else feels that everybody else that got co-located on the same hardware with that person gets less resources. So you want to move that person out. And what you can do in Citus is online tenant isolation. The SQL is on the slides to how to do that. But essentially, you can tell the system that specific tenant, please split up the shard in the middle where that tenant is, and that will turn the shard into 3 shards, where you will have a range of tenants on the left, a range of tenants on the right, and that single noisy neighbor in one shard. And then you can move that specific one shard into a separate node and keep it away from everybody else on a new machine that you just added. And speaking about adding machines, you can scale out both horizontally and vertically. You can add more CPU resources, or you can add more machines. And when you add more machines, you have, when you add more machines, you don't immediately get the benefit of the storage. Of course, new writes to the system will be automatically distributed to new machines that you add, but the existing data may not be. And for that, you have to rebalance, which is a process that looks at the whole cluster, and based on the strategy that you picked, will decide how to move the shards between the nodes. And it can move them by looking at the total size and trying to balance out the storage used. Or you can look at the amount of shards, or you can implement your own strategy. For example, you could use the upcoming CPU utilization to devise a strategy based on CPU utilization. And that may or may not make sense, because maybe you don't want to move terabytes of data every time the CPU moves around, but you can devise, like in some systems that may make sense, depending on your data sizes, load changes, and you can also always look at bigger windows of time. So in Citus, you just Citus Rebalance start, and that will move the things around. And since Citus 11.2, you have JSON-B pretty details from Citus Rebalance status to get nice JSON output that you can throw into your Grafana dashboards and visualize how the data is being moved around the cluster. So we are trying to make everything explicit. And since we are running out of time and we want to go to questions, I will finish up right now.
We finished.
Well,
anyway.
yeah, we sped up in the middle, so we have more time for questions.
No?
Are there any questions? Alicja?
Yeah, PostgreSQL like was. Oh, sure. So how this is, the question was how this is different from the PostgreSQL project. So I believe like the project actually was abandoned pretty much. There is like new, because PostgreSQL, as I remember, like it's owned by EDB, and EDB now it's like more going into BDR, which is like another project. So this is in concept actually that was pretty much similar, like in concept, in the concept layer.
Any more questions?
Oh.
Okay.
Thank you then.
Thank you all.